So welcome to Robotics 2. We are going to build upon the coordinate frames that we studied in last few lessons to get a little bit more detail into the kinematics and dynamics of the aircraft. Kinematics is just study of motion, which is displacement, velocity, acceleration, and roll, pitch, yaw, orientations, orientation rates, and acceleration, angular accelerations. Dynamics is where the inertial effects, the forces come into the picture. So first and foremost, what are the most important aircraft variables? And these aircraft variables are very, very important. And it may take some time to get familiar with the aircraft variables, but I will try to explain these aircraft variables in detail. So please try to understand that so far we have lots of frames. A quick recap. The very first frame is going to be the inertial or fixed frame. Do you agree with me? Ground speed or velocity of the aircraft with respect to ground, which is fixed, is expressed in the inertial frame. So which means Pn, Pe, and Pd, these are the inertial north position of micro or miniature air vehicle expressed along ith in Fi. So please understand that these Pn is the north position of the aircraft in the inertial frame. The inertial frame is earth center, earth fixed, not rotating. So earth aircraft distance is measured with respect to the fixed frame. So Pn is the inertial north position. Pe is the inertial east position, and Pd is the inertial down position. And these positions, Pn, Pe, and Pd, is expressed in the inertial frame. So inertial frame is the fixed frame. So this is inertial frame. So you have this inertial frame that is fixed, and I'm going to show it somewhere over here. So this is my inertial frame. This is my inertial frame. And this is, again, this is U. So this is going to be north. This is going to be east. And this is going to be down. And this frame is fixed. Now, the second frame that is attached to the vehicle is the vehicle frame. So basically, what you have is you have this vehicle frame. And in this vehicle frame, what you have is you have translated the frame. This is the inertial frame translated to the vehicle frame, and the distance from the inertial frame to the vehicle frame along north direction is Pn, along down direction is Pd. It could be negative. Along east direction, which is Pe. Now, after vehicle frame, the first frame that you get is the vehicle 1 frame. After vehicle 1, you get vehicle 2 frame. And after vehicle 2, you get body frame. So now we are going from the vehicle frame, and we have these rotations. So the rotations are yaw, pitch, and roll. So I have these respective rotations. These respective rotations are about their individual frames. So please understand, I have these 3 rotations. Roll angle is, so let's start with first. So first I have this yaw angle that is defined with respect to vehicle frame. Then I have pitch angle that is defined with respect to vehicle 1 frame. And then I have this roll angle, which is defined with respect to vehicle to frame. So what I have is, I have this vehicle frame, vehicle 1 frame, vehicle 2 frame, and I get to the body frame. So I have these three. So these three are the roll, pitch, and yaw angle, or yaw, pitch, and roll angle. If you look at the way we are going from vehicle frame. FB stands for vehicle frame. From vehicle frame, we go to vehicle 1 frame by rotation of yaw. After vehicle 1 frame, you go to vehicle 2 frame by rotation of pitch. And then from vehicle 2 frame, we go to the body frame after a roll rotation. Everyone understood this? We spent a lot of time on that. So now we are in body frame. Now in body frame, what we have is, this is very important. Aircraft has some velocity. It has velocity U, velocity V, and velocity W. These aircraft velocities are expressed in body frame. So U is the velocity expressed in the body frame about its I, or the north axis. V is the velocity of the aircraft expressed in the body frame along J axis. Please note, I is in the body frame, J is in the body frame, and K is in the body frame, and these are the respective aircraft body velocities. So these are body velocities. Everyone understood this? So what it means, and I need to emphasize this, is we cannot solve everything in one shot. What we need to do is, we need to separate out these motions. So for an example, I have this aircraft. This aircraft, this is my inertial frame. This aircraft is over here. So I have north, east, down position with respect to this fixed frame. Now, once the frame that is attached to the aircraft is my vehicle frame, then I do yaw, get into vehicle 1 frame, then I do pitch, I get into vehicle 2 frame, and I do roll, I get into the body frame. And now the U, V, and W are with respect to this oriented body frame. Everyone understand? So what we have done is, first we took care of the aircraft attitude, and then when the aircraft is in body frame, we are looking at the aircraft velocities in U, north, east, V, and D, down. Everyone understood this? If the aircraft is going up, clearly your down velocity is going to be negative. But at the end of the day, please understand, now the aircraft is oriented in the position that comprises of yaw, pitch, and roll. And that is where the aircraft is going. Everyone understood this? Okay. Now the next important part is, you have P, Q, and R. As aircraft, see, right now what has happened, that aircraft has oriented, now aircraft is in the body frame. In this body frame, this is actually an object that has 6 degrees of freedom. 3 degrees of freedom are 3 translations, and last 3 degrees of freedom are 3 rotations. So 3 translational velocities are U, V, and W, U, V, and W, and the rotations about north or X is P, rotation about the east is Q, and the rotation about D is nothing but R. So this aircraft has 3 rotations, which is basically north, so P, then Q, and then R. So these are PQR are the body rotations. So these are the body angular rate or angular velocities. So I will repeat this once again. Pn PE, PD are the inertial positions. So where that aircraft is. Then U, V, and W are the body velocities. And P, Q, and R are the body angular velocities. And Phi, theta, and psi, Phi, theta, and psi, those are called as Euler angles, or that is called as altitude of the aircraft, because those are the roll, pitch, and yaw angles that are calculated to define the orientation of the aircraft. Everyone understood this? So I need to write this down. The first is position. Second one is body velocity. When I say body velocity, this is in body frame. And these angular velocities are again in body frame. And these roll, pitch, and yaw are with respect to vehicle, vehicle 1, and vehicle 2 frame. Everyone understood this? This is very, very important. Now, here comes an important problem. Any aircraft typically would have 3-axis accelerometer and 3-axis gyros. It's called inertial measurement unit. Inertial measurement unit is a strap down unit, which means it is actually fixed onto the aircraft. So the angular velocity or the translational velocities that are measured by this inertial measurement unit by integrating the angular velocities or integrating the accelerations is in the body frame. So which means if you have a sensor which is strapped onto this aircraft, it is going to give you the sensor measurement U, V, W, and P, Q, and R. Everyone understood this? Now, let me pose the other problem. Imagine if I have a GPS device on that aircraft. If I have a GPS device on that aircraft, GPS, after all the calculations, is going to give me PN, PE, and PD. Everyone understood this? Now, I want you to understand that I need to get the values of PQR, integrate those, and find out roll, pitch, and yaw. So finding out roll, pitch, and yaw from PQR is nothing but solving the kinematics problem to find the attitude of the aircraft. Now, we are going to use all these 12 states to derive first kinematics equation of motion, and then we will gradually move on to the dynamic equations of motion. So this chapter is very important because, believe it or not, whether it's a fixed wing plane, so basically this is an X-plane, so or if it is like a pusher plane, or if it's a plane like V plane, or it may be any flying vehicle, you would use the same 12 states to define the kinematics and derive dynamical equations of motion. Any flying robot, these are the 12 states that will describe the complete behavior of the aircraft. So remember this. But the problem here is first 3 variables, which are the position variables, are defined with respect to inertial frame. Body velocities and body rates are expressed in the body frame, and the altitude solution, roll, pitch, and yaw that we have to calculate is with respect to their own rotation frame. Everyone understood this? That is something that I want you to remember. Now, translational dynamics. So we have PN, PE, and PD. That is the position in the north, position in the east, and position in the down direction, P north, P east, and PD. These positions are in inertial frame. It's inertial frame. Now, what I want to do is, so here is something I want you to let me emphasize this here. Imagine that this is my northeast down frame, and I'm going to show it like this: north, east, and down frame. So if I say this is my north, this is my east, north, east, and down frame, it's fixed. And I'm going to show you that the aircraft vehicle frame as just the CG of the aircraft. So this is the CG of the aircraft. And then what I have is I have these three vectors. So if you think about it, I have this guy, which is PE. Then I have maybe P, it draw nicely. So I have this PE. Then I have this PN. And say I have this PD. So these three vectors are with respect to the fixed frame. Everyone understood this? So if I were to take the derivative of these displacements, I would get velocities. Everyone agrees with me? And this equation is valid only because the frame in which those displacements are expressed is not rotating. And I will repeat this once again. If I take the derivative of these displacements, I would get velocities. And this equation is valid because my frame is not rotating. But what I want is, I want to express, now here is the problem that I have. I have my PQR UVW in the body frame, but my PN, PD, and PE are expressed in the inertial frame. So when I take the derivative, I get the velocities in the inertial frame. And I need to transfer or transform those velocities in the inertial frame into velocities in the body frame. Remember, dollars to dollars, pesos to pesos. So what we have is we have a rotation matrix. That rotation matrix, what is going to do is it's going to transfer. And so what I'm going to do is it is going to transfer these velocities. So I will write this down. So velocities in inertial frame need to be transferred to velocities in the body frame. So I would write down, and I will write this equation just for clarity here. These velocities. Now I have to go from inertial frame, or in other words, the vehicle frame that I have here is vehicle frame to body frame to get U, V, and W. So what I have here is I have this guy. This will take me from the inertial frame to the body frame. And that rotation matrix we have already derived in last class. And that is, so if you think about it, this is the velocities in the body frame, body. So I need to have R body V is equal to Pn dot, Pe dot, and Pd dot. Because this needs to be in vehicle frame. This is the rotation transformation multiplied by U, V, and W. They are in body frame. This is exactly same as you have a vector in body frame, multiply with this transformation, and you get the vehicle vector in the vehicle frame. So this is the transformation that we derived or we looked at in last class. And that transformation is nothing but 3 successive rotation matrices that we studied. So what you have is, and I need to, I think I kind of showed you this, but this matrix is the product of rotation matrix about yaw, rotation matrix about theta, and the rotation matrix about rho. So these 3 rotation matrices, when you multiply, you get this combined transformation matrix that gives you the relationship between the inertial velocities and body velocity. Everyone understood this? And let me clarify once again what that means, because this point is actually very important. You have an aircraft. For a minute, just imagine you don't have any GPS signal. Okay. What you have is you have accelerometers in 3 directions, X, Y, and Z. They are going to measure accelerations. Accelerations are going to be noisy. Imagine you do very good filtering and you try to get rid of the noise. You integrate the acceleration once. You integrate the acceleration twice. So now what you have is you have the position. You agree with me? But if you think about it, those positions are calculated after the successive rotation. Remember, we have these rotations. We have these rotations. So the accelerations that we have, they are in this frame, the body frame. So what I need to do is I need to get these accelerations in the body frame, integrate those, and then transform those positions back into inertial frame. So that is what is happening over here. So this rotation matrix will take the accelerations or velocities or integrated accelerations into the body frame, use the rotation matrix and transfer it back. However, there is a small problem, because please understand, this aircraft is not going to fly at the fixed roll, pitch, and yaw. What it means is as U, V, and W, they are changing, roll, pitch, and yaw will also be changing. What it means is you will have to compute the solution, the resulting solution, every milliseconds, so that you have accurate representation of the north velocity, east velocity, and down velocity. Everyone understood this? Now imagine at this point, the acceleration data that you are getting is noisy. Clearly, with the noisy acceleration data, you will have error in the calculation of UVW. You will have error in the calculation of Pn dot, Pe dot, Pd dot. And you integrate those further, so you are going to have error in Pn, Pe, and Pd. When you have this solution, Pn, Pd, and Pe, and once you feed that to the GPS solution, you can use this external reference to correct this solution, Pn, Pd, and Pe. And that is basically nothing but the sensor fusion. You have a sensor accelerometer that is not in the same frame. It's giving you some output that is noisy. You integrate that, you find the solution, and use an external reference to correct that solution. So this is the translational dynamics. And please understand, this equation works because the frame is fixed. The frame is fixed. Now, let's talk about the rotational transformation. And this rotational transformation is exactly same as, remember, we talked about the Jacobian when we have multiple frames. So how did we do it? We said, and I'm gonna write this on the side, we said omega x, omega y, and this for robotics 1, omega z. These are in the inertial frame, which is the first frame for robotics. Yeah. Yeah, because GPS data comes to us at 20 hertz, which is 20 times a second. But the accelerometer data we get at 1000 hertz. So which means, so aircraft flight control system cannot update the control surfaces at 20 hertz. They have to update the control surface. The solution has to be computed at minimum 1000 hertz, 1000 times a second. Otherwise, the aircraft will go out of control. So what we have is, we have an external solution that is coming at much slower update rate, but internal solution we are calculating at higher update rate, and then we use it to correct our internal solution. Yeah.
While integrating, there's a constant, so it's not noisy noise is included with the integration, but what happens with the constant?
Okay. So that is also a good question. So if I have a noise, so you have an acceleration. If I want to find out the velocity, what I do is, velocity is derivative of acceleration. So just imagine if I have a constant acceleration, this is going to be a times t. If I do a constant, if I do the velocity, integrate the velocity and try to find position, what I have is, I have a t square by 2 plus a constant plus t plus another constant. Now imagine if this guy acceleration is not accurate. So acceleration is not a flat line. Instead, this acceleration is kind of changing and going up and down, up and down, up and down. These teeny tiny changes, that error, so that error will get multiplied by t square by 2, and t is continuously increasing, which means that initially, even though your error may be very small, but as time goes on, the integration of error is going to be very, very large. What it means is, if you have, you can think of actually a lot of smartphones have IMU apps. So you place the smartphone on a flat surface and try to find the position. You will see that as the time goes on, the position will keep on increasing even though your smartphone is not moving. That is purely because of the error that is caused due to noise. So noise gets integrated, time increases. So wing deflection and all, we are not talking about control surfaces yet. So right now we are not worried about, we are assuming aircraft is completely rigid. Okay, so noise sensors are noisy, and we use some smart sensor fusion algorithms, Kalman filtering, particle filtering, and variations of these filters to minimize the error. Coming back to the point that I was trying to discuss. So in robotics 1, if you recollect, this is the equation that I wrote. Omega x, omega y, omega z are the rotations about the inertial frame, rotation rates about the inertial frame. And these are given as, if you remember, so 0 r 0, then you have 0 0 theta 1 dot, plus 0 R1 0 0 theta 2 dot plus 0 R2 0 0 theta 3 dot. Remember, it's something like we talked about this and then we solved this equation and found the Jacobian. So remember this equation written on the right hand side in robotics 1 to find angular rates. What we did is we used the rotation matrices, and then in robotics 1 with our convention we only use the rotation about z axis. So you can see theta 1 dot is at the z location, theta 2 dot is at the z location, theta 3 dot at the z location, but you have the relative rotations. 0 R0 is identity, 0 R1 is basically you compute by the rotation, and 0 R2 again is 0 R1 1 R2. So this guy is 0 R1 and 1 R2. 0 R1 and 1 R2. Remember this we did in robotics 1. We are going to use the exact same approach to find out the rotation kinematics. And for rotation kinematics, we are using these rotation matrices. And please understand, the first term is an identity matrix, 0 R0. Second term is the rotation in vehicle 2 frame that is transferred to the body frame. Then you have rotation in the vehicle 2 frame multiplied by the rotation in the vehicle 1 frame multiplied by the rotation, your rotation. Everyone understood this? This is exactly same as what we studied in robotics 1. The only difference here is, please understand that this PQR is in body frame and these individual rotations are in their respective frame. So what we have here is this rotation matrix is taking this rotation and converting that into the body frame where you have P, Q, and R. This rotation is in vehicle 1 frame. Vehicle 1 frame gets transformed to vehicle 2 frame. Vehicle 2 frame gets transformed to body frame, and then that is where we have it. Can you see vehicle 1 frame and vehicle 2 frame? So these frames get cancelled, which is exactly the same equation that we looked at in robotics 1. Everyone understood this? Any questions here or not? If you have not attended my robotics 1, please go on to YouTube, and there are videos for robotics 1. Just look at the rotation calculation of rotation rates, omega x, omega y, omega z in the lecture, and you will see that I have used the exact same technique to find out the rotations. Everyone understood this? If you have not understood, ask me now. This topic is conceptually very, very important. Everyone understood this? Any questions? So please understand those individual rotations are in their own respective frames, and those frames finally need to be converted to the body, because PQR, just like UVW, are expressed in the body frame. Now, what I want to do is, I just want to introduce these respective rotation matrices. So I have the rotation matrix BRV2, and I have this product of rotation matrix. Yeah, there is a question. Okay, so is there any question? Okay, I thought someone raised hand. So, okay. All right. So this rotation matrix is the matrix this shown over here. And when you perform this multiplication, what you have is you have a very simple equation P Q R is equal to this transformation matrix. And again, this is an orthonormal matrix because this is the rotation matrix. So you take the transpose of this to get theta dot, phi dot, and psi dot onto the left hand side. So this matrix, if I were to call this R, what I do is I have R transpose that relates PQR to phi dot, theta dot, and psi dot. Everyone understood this? So the two important set of equations that describe the aircraft kinematics are this first equation that we have shown over here and the second equation that we derived over here. So these 6 equations, they give you the rotation transformation and the kinematics equation. Here is something else that I want to talk about. How do you solve these 6 equations? And let me show you these 6 equations. And you can spend your entire career working on these equations if you are a guidance and navigation engineer. So we have equations for velocities. So we have equation for translational velocities. So this is the translational velocity. And we have rotational velocity. It is extremely important to note that these 3 are measured by the sensors on the aircraft. So you can have an IMU, which is 3-axis accelerometer and gyroscope. That will give you accelerations and you can integrate those accelerations and find the velocity. The way to solve these equations is first, we solve the equation for rotational velocity. Once we solve the equation for rotational velocity, please understand that equation is a differential equation, which means we have to integrate that numerically. Now, what do I mean by numerical integration? Initially, here is how we start. First, we assume that the aircraft has 0 pitch, 0 roll, and 0 yaw. When aircraft takes off, the gyroscope is going to measure some P, some Q, some R. So we will iteratively find out theta dot, P dot, and psi dot. So this is how it will go. At time t is equal to 0, roll is 0, pitch is 0, yaw is 0. So basically, those values are substituted in this matrix. So this matrix is known. At time at 0.001 second, which is 1,000 of a second, you get an update from the gyroscope. You get a gyro measurement P, gyro measurement Q, gyro measurement R. You use the previous rotation matrix. You use the previous rotation matrix to update the value for P dot, theta dot, and psi dot. Everyone understood this? You get P dot, theta dot, psi dot. You multiply that by the time step. That gives you P, theta, and psi. Do you agree with me? This multiplication approach is valid because the time step is very, very small. it's so 1/10,000 of a second. The time step is very, very small. So that's why you get some value of theta, some value of psi, and some value of p from the previous time step. Do you agree with me? Now, what you have is this, you get the P, Q, and R for the upcoming time step. So you use the previous roll, pitch, and yaw values to compute the rotation matrix. You get these new values of P, Q, R, use the previous computed rotation matrix and get theta dot, P dot, and psi dot. You understood this approach? So this is sort of a recursive approach of numerical integration. And this approach works because your time steps are very small. So you are integrating these equations at 1000 hertz. Again, yeah.
Then technically the calculation on this one.
Yes, it's basically it's a digital data coming in. So basically you are doing discrete integration at every time step, but it is continuously done. Still there are problems because the integration scheme that I just explained, if you remember, it is something called as the Euler integration. And Euler integration can suffer from numerical instability. So you can use some type of a trapezoidal rule or some kind of Runge-Kutta method to improve the numerical stability of this algorithm. So which means all of a sudden is in a fraction of a second, all of a sudden, if aircraft performs say a 180 degrees roll, pitch, yaw, that type of maneuver, the integration that you are performing, the Euler integration, will go out of bounds. So what you do is you basically use some type of Runge-Kutta or some technique. Now, what you are going to do is you are going to find out the roll, pitch, and yaw, theta, phi, and psi value at every time step. That value gets fed into the top matrix where it needs cosine phi, sine phi, all that stuff. So these equations are solved recursively but together, because you are going to get UVW, you will get PQR from the sensor, you will integrate it, you find out the roll, pitch, yaw, feed that into the top equation, and then actually recursively get this input and then find out Pn dot, Pe dot, and Pd dot. Everyone understood this? That is very important. So what we are going to do is, once your aircraft model is done, first, before we implement the dynamics, we are going to just implement the kinematics, which means we will have these 6 equations. We'll numerically integrate these 6 equations, and at the end, what would be the output of these? At the end, I'm going to get P, Q, R, U, V, W from the sensor, and I would be computing Pn, Pe, Pd, and roll, pitch, and yaw, and I would feed these states, these 12 states, to your aircraft model, and you will see that your aircraft would fly. But it would just purely kinematic representation. We will not take into account the inertial effects. We will not take into account the aerodynamic forces. We will not take into account the control surface deflection and propeller thrust and all. So we'll subsequently keep on adding that stuff. So I want to discuss this part, and some of you might be familiar with this, but I want to emphasize on this because some students are taking this course after 547. So for my own satisfaction, I need to cover this. So imagine differentiation of vector. So in the first class, we talked about what the vector is. So imagine, okay, what is a vector? Okay, correct. Direction and magnitude. So I'm going to call a vector P of x. This vector will be given as, say, P, and I have a unit vector I, where P is the magnitude, I is the indicating the direction. This is a vector. So what I'm gonna do is I'm gonna draw an arrow. So something like this. This is I and this is J. And I'm gonna say this is my P. If I take the derivative of this vector, if I take the derivative of this vector, Px dot, what that means is I need to take the derivative of magnitude u times v rule, P dot I plus P I dot time. So if I take P, so P dot x is nothing but d by dt of Px. So this has two components. First, I need to take the derivative of the magnitude, and then I need to take the derivative of vector. Now let's look at a case where the vector P is expressed in the inertial frame. What do I mean by inertial frame? In inertial frame, this frame is fixed. If this frame is fixed, clearly I could have a change in the magnitude, but clearly the direction is not going to change, which means the derivative I dot is going to be 0. Do you agree with me? So this is very simple. If I have a vector that direction is not changing, then the rate of change of displacement is velocity. Are you okay with this concept? Now here comes the tricky part. Imagine, this is very important, I have the same vector. Okay, I have the same vector and I have something like this. So it's the same vector P. Again, this is frame I, this is frame J, and believe it or not, there is a frame K. Right hand thumb rule, X, Y, Z. And now the frame is rotating at velocity theta dot. Now I want you to understand the difference between this guy and difference between that guy. What I have is here, the coordinate frame is fixed. There, the coordinate frame is rotating. And now what I want to do is I want to find out the derivative of vector. Now what I want to do is I want to find out the derivative of vector. I'm going to start with the same equation, Px. And I would say it is P times I. And I will again, using u times v rule, I will say P dot I plus P I dot. Are you with me? I agree with the first term because the length of the vector could be changing. The length of the vector could be changing. What about the second term? In the case when the coordinate frame is rotating, when the coordinate frame is rotating, would I dot be 0? I dot is not going to be 0. Why? Because I is changing with respect to time. And when I is changing with respect to time, it's going to have some type of derivative. Are you with me so far? So the question is, how do I find out the value of I dot. The value of I dot, and remember this, if you have taken classical dynamics, they will make this super complex and they will ask you to solve using a cross product and matrix product.
Wait.
But I'm going to give you a simple rule, which is called circle of vectors. And remember this. Can you see that this rotation is about K? Is this rotation or rotation rate positive or negative? Curl your fingers in the direction of rotation. Thumb is pointing towards positive K axis. So do you agree with me? Theta dot rotation is positive. Curl your fingers. Okay. So what I have is I'm going to say my omega. Omega is the angular velocity of the frame. Angular velocity of the frame again is given as plus theta dot K. And it's an angular velocity. Remember velocity, angular velocity. So it has magnitude and it has direction. You agree with me? Whenever you have a derivative of vector, whenever you have a derivative of unit vector, the rule is take the frame angular velocity and cross it with the vector. So what that means is I will write this over here. I dot is equal to omega cross I. So omega cross I. So I'm going to define what omega is. Omega is theta dot K cross I. Now what has happened here is theta dot times theta dot K is omega crossed with I. I don't want to see K cross I. I want to calculate what this product K cross I. So remember circle of vectors. So there are three vectors: I, J, and K. And we are going from I to J, J to K. So this is the direction that we are going. Now, pay attention. I cross J is K. I cross J is K. J cross K is I. K cross I is J. And if you go in the opposite direction, so for an example, if you go J cross I, you are going in the opposite direction to the circle of vectors. It will be minus K. K cross J. K cross J is minus I. And I cross K. Can someone tell me what is it? Minus J. Everyone understood this? So K cross I is going to be J, right? K cross I is going to be J. What it means, and I want you to understand this, it is extremely important, is I'm going to write this equation down as P dot I plus P, and I would substitute here theta dot J. Are you with me? Plus P theta dot J. And this equation is so important that I'm going to rewrite this on the board to explain it. Because what I want to do is, after I draw this here, I want to show you a demonstration. That way you won't forget this. So you have I, you have J, and you have K. And this frame is rotating at theta dot. And what you have is, you have a vector which is Px. Now, what's going to happen is, I want you to think about it. Imagine for a second that this is the point. This is just a simple mass. And this mass is traveling across x-axis. This mass is traveling across x-axis. If my frame is fixed, the speed of this mass will be px dot. Do you agree with me? If my frame is fixed, if I'm an inertial frame and px is extending, I don't know if online students can see this, but if px is extending, velocity of this mass is going to be px dot. Now imagine if the frame is rotating and this mass is going forward. What would happen? This mass will not only go forward, but it will also go up. Do you agree with me? The mass is going. Can I turn off the video? Well, unfortunately, that's why I said come to class. So what you have is, you have a component of velocity, which is px dot, which is extending around x-axis, and you have component of velocity, which is px times theta dot about j-axis. So if I were to write down px dot, the expression is px dot I plus p is the radius, px theta dot j, and j means this guy is in the same direction as j. So can you see that I have a vertical component of velocity and I also have a horizontal component of velocity? Everyone understood this? That is nothing but differentiation of vector in two reference frames. Yeah.
What is the rotation about y-axis?
That is all right. So now what you do is, this is, logic remains the same. No matter, now there is a frame rotation. So I'm going to write frame rotation theta, I'll call this theta z, and I will call this theta y. Okay, theta z and theta y dot. Do you agree?
About y-axis.
I-axis rotation is not going to give you any problems. I-axis rotation has no radius, so there is no velocity. So even though it's like this, it will still go straight. Are you asking about rotation about this?
I asked about y-axis.
Okay. Let's do it. Let me show you. So, theta x. Happy? The rotation of the frame, omega frame. And please remember this, because this is extremely important. I'm going to write this down as theta x dot I, because this is the rotation about I, plus theta y dot j plus theta z dot k. Do you agree with me? My vector is p of x, which is px I. Px dot d by dt of px, I would write this down as px dot I plus px I dot. Now I dot px remains as is. I dot is omega frame. And why this is important? Because exact same equation will appear when we look at the dynamics, when we write. Yeah, question?
They said they just, in the settings for your video, they just, the background is on blur, and that's why they can't see the screen.
See, for robotics too, you should come to class. That is absolutely important. Omega F, where was that? Okay, omega F cross I. Everyone clear up to this point? Next step, Px. I'm going to substitute this guy. And please remember this, because next class, I would just use this result to derive the rate of change of momentum. Because please understand, momentum is also a vector. Same logic applies, no matter what vector is. If you have the quantity expressed like this, take the derivative of the quantity, derivative of the unit vector. So this will become theta x dot I plus theta y dot j plus theta c dot k. And I have to tell you that all these rotations are positive. That's why there are positive signs. There is a reason there is a positive sign. If these rotations would have been negative, I would have written negative. Okay, multi-cross I. And please note, we are taking a cross product, which means the order is very important. I cross j is not same as j cross I. Order is very important. Now plus Px theta x dot I cross I is, what is I cross I? 0. So 0 plus theta y dot j cross I. J cross I minus k. J cross I which means now, since you have frame that is subjected to rotations about 3 mutually perpendicular axes, you have the result Px dot I. Px theta, so first guy is 0. So Px, this becomes minus theta y dot k plus Px theta z dot j. And at the end, if you look at this, this is the radius and this is the angular velocity. So this equation is something as simple as omega times r. But and now let's visualize. So I have a rotation about theta dot, and this mass is going forward. The rotation about theta dot, would it give it any velocity in any mutual perpendicular axis? No. So its translation is not going to get affected. If I have a rotation about z, this mass will go up. Do you agree with me? If I have a rotation about y, what will happen? This mass will go in this direction. Do you agree with me? And this direction is opposite to the positive k direction. That's why we got this negative sign. Everything checks out. Everyone understood this? Same logic we would apply when we take the derivative of angular momentum. Remember Newton's second law? Rate of change of linear momentum is force. Rate of change of angular momentum is torque. Same logic. Same thing, except then what I'm going to say is, instead of expressing vector as Px, I would have an H vector, Hx, angular momentum about x. And then I'm going to take H dot x with the same logic. And you will see that a frame rotation will play an important role. And just to tell you, it's coming in the next class. So rotation, I want you to see here. These equations, can you see that omega b cross j cross b, that term? that is what is happening here. So same thing is gonna come bite us again. So make sure that you understand this development. So rotation dynamics will comprise of the equation, and don't worry about these J's and taus and all those are just constants. I wouldn't worry about those. But the most important equation that I want you to remember is omega b cross b slash I cross j b bi. So because the frame is rotating, you have this omega cross unit vector as in the equations. Okay, let me okay, background blur cannot see. Can you see my online students? Okay, now what I'm going to do is I'm going to stop here, but I'm going to show you my solution for the spacecraft. And then if you have worked out the solution, you are welcome to correct your solution. And then I'm going to show you my solution for the aircraft. So if you have worked out the aircraft solution partially, this would be an opportunity to correct your solutions. So I'm going to stop here. Well, I will continue to record. So class is done, but I'm going to explain the solution of the spacecraft and the aircraft. So if you already have worked out the solution, then you are welcome to leave. If you want to see the solution, I will show you the solution here. And the book has a GitHub, so you can go onto the GitHub and download the code for the spacecraft. And let me show you the code for the draw spacecraft. So as you can see, now it will all make sense. The input to the spacecraft is PN, PE, and PD. Remember, those are the values that we just found out. Then U, V, and W. Those are the values we are getting from the sensor, which means if I say that my aircraft is going in the level flight at 10 meters per second, what will happen is I would substitute U is equal to 0, U is equal to 10, V is equal to 0, W is equal to 0. Then next part is P, theta, and psi. Those are the roll, pitch, and yaw angle that we find by integrating the kinematics equation. And then last we have PQR, which are the body rates, and I have the last term, which is time. If you go down, I have defined the persistent variables: spacecraft handle, spacecraft vertices, spacecraft faces, and face colors. And then this is the equation. This is what I'm using when I'm calling for the first time. And this code is available on GitHub. Okay, so you can download the code and try to run it. It will run. And then I actually use a spacecraft handle. This is not the only way to do it. You can do it slightly differently. That's totally fine. Then you can add this label X, Y, and Z axis. And then what you do is for every time step, a student asked me that the spacecraft is not getting redrawn. So please understand, you will have to add this at every time step. You will have to redraw the base. So basically, you will have to call this function draw spacecraft body in every time iteration. Go down, and then this is where the function handle is, which is draw spacecraft body. That is computed every time. And now you have roll, pitch, and yaw angles. Then you have the north, east, down displacements. And what you need to do is you will have to perform the projection matrix transformation so that the MATLAB X, Y, and Z. MATLAB X, Y, and Z are like this, and your X, Y, Z are north, east, and down. So you have a negative turn, and your signs X and Y are flipped. So that's why you have this transformation matrix. Can you see? You have one here, that is indicating that your north is down and MATLAB X, Y are flipped. And can you see the Z axis is negative because you're down, your axis are down positive, but MATLAB's going up is positive. So go, and then what you do is go down, then draw now. And then you have these rotation matrices. Please understand, these are the exact same rotation matrices. Rotation about X, rotation about Y, and you have the rotation about Z. And then you are finding out this direction cosine matrix, which is the product of roll, pitch, and yaw. And I want you to understand the order is very important. How are we rotating? First, we are in the vehicle frame. First, we have a yaw rotation, then we have a pitch rotation, and then we have a roll rotation. So that's why the first matrix on the right hand side is yaw. That gets multiplied with rotation of pitch. That gets multiplied with rotation of roll. Everyone understood this? Because we are going from the vehicle frame to body frame. Vehicle to vehicle 1, vehicle 1 to vehicle 2, vehicle 2 to body, in that sequence. And then going down, you actually translate, you do the translation, that is just translating based on, and then this is the code that is actually drawing the spacecraft. Are you with me so far? Now, what you need to do is copy the whole code as is and replace this V with this V. So this V. So your aircraft has 17 points. And you have to give the coordinates of those 17 points. And actually, here I gave the coordinates in terms of the lengths, like fuselage L1, fuselage L2, fuselage L3, wing 1, then fuselage tail wing by W by 2. You are welcome just to input the numbers. And once you make that change, then instead of spacecraft, it will draw aircraft. And everything else is going to remain the same. And you have to just define, if you want to define, you can define different Fs. You don't have to take picture. I'm recording it already. So, and I will upload the video by tonight or tomorrow. So, okay. And then you can define the colors. So the only code that you will have to change is you will have to change this function. And I did not change. So basically size 50 is just to scale the aircraft. You can change the scale to 2510. That will make your aircraft bigger or smaller. Then define all these lengths. I just added these colors so that the aircraft looks nice. But you don't have to add. MATLAB will just draw it in blue. And then you have these vertices and faces. And then the last is the coordinates of those points. Okay. Any questions? Can I stop recording? Yeah. Yeah. This?
Yeah,
Okay. What about that?
that's not from the drawing, spacecraft from right?
This is the aircraft drawing.
Okay, so we will have to,
So first part is just drawing the spacecraft, right?
Right.
Second part is we are going to draw the aircraft. So what I want you to do is, in the assignment, I think I gave you to draw aircraft.
Yeah.
So you have to take that spacecraft code and replace with this guy. So instead of spacecraft, we'll draw the aircraft. Okay, I'm gonna stop here. Chat window. Yeah,
I was able to get the spacecraft looking like this with the 16 points with this.
yeah, that would be fine.
It looks a little bit different as if fine. And for turning it in, you want the MATLAB and simulation. That's it.
Okay, chat window. Okay, Austin, good job, man. Now you know.
Sir, the email from Mother TA, are you gonna consider that?
What?
Jacob has sent an email, right? Regarding this. Not required, right? Or do you want it like this?
Fine.
Yeah, like why? Extra effort, why? Everything's there.
He's not gonna grade, you're gonna grade, right?
Oh, yeah.
So you are okay, whatever, so you can send whatever format you are comfortable with. Okay, Jacob, he is actually gonna do the grading. You can help them with the code and other stuff.
I put it now.
Huh?
I put it now.
Okay, yeah, so he will do the actual grading and don't spend too much time.
That's what I was saying, about submission.
You can coordinate with him and then post the announcement. That's totally fine.
Did you read that email?
Yeah, sir, I saw that.
Okay, I'll put an announcement out.
Okay,
That's gonna
yeah,
be great
question?
for the
Is it
audience.
okay?
Yeah, that's a good start.
Oh, yeah, that's good.
Do they have the code submitted? Sure. You know,
And sir, do you have,
Simulink code
does sir have any Excel sheet to keep the track of grades?
is already going to announce how he wants it. I think he wants it in zip file. You can, Tatvik, you have access, right? To the Canvas. You can send everyone the email how you want it.
And one more thing, do we keep the track of grades in Excel file or something like that?
No, you just go ahead and enter there.
Oh, okay, direct.
Jacob, you can show him where to enter the grades.
No, I know how.
You know how to enter the grades.
And one more thing, do you want to include this project?
What project?
This is something that I did last year.
But this is,
AG. Like everything that I watching that is there.
I know, that's okay. Question? Yeah, question, yeah.
So I have, my vertical stabilizer was inverted because I had this positive distance. So it was a problem. But I have this else code for redrawing at every time frame. But when I run. So I have my aircraft. I modify this.
For office.
No, it doesn't update. But if I
Doesn't
pause,
Okay,
it updates.
yeah, so I will show you my code. You are missing one line.
Okay.
Does your spacecraft update continuously or no?
No.
Yeah, so that is the issue. So your spacecraft, I'll show you my code.
Is it a Simulink lineup?
No, it's a MATLAB lineup. So this is my aircraft code. Yeah. So check.
Sir, did sir run the project for the drone? Okay. Bamboo drone project.
Yeah, you have question.
So, basically,
What I did was just the hovering that he's gonna do.
do you want to?
And what other things that you can do is on the culture. You know, the camera.
Previous.
There is camera. There is single. There is single.
So we have to set it up.
Then
So this was
MATLAB.
the area, the animations from the software. But the problem is.
Animation doesn't work because this is the box frame.
Yeah, so my
Yeah, no, sorry.
this, once we turn in the, if it's.
Yeah.
free,
We have a back.
Once we run it, that's when it.
You have.
It needs to It needs to do the aircraft. So what we need to do is we need to take the spacecraft photo and then change that to the aircraft that I just explained.
It's like
That would be under this
PX, PX dot, that's the initial start that you have. So you moved you moved in that direction further, that distance. and then
These are the points that are
PX
drawing the
dot.
spacecraft.
It's basically just the rotation of delta.
Aircraft is 15 points.
So usually it's like. Saying
So
like,
this is where
it's
this
a-
entire
it's an angle, so it's angle delta. So basically it's.
You have to change this code with the code that you draw the
Since then you would be, you'd orient.
surface, yeah.
There would be some.
Surface.
Yeah, you would have.
No, there is no
One if the orientation sticks, the orientation sticks, then it would just stay the same, but I guess I presume the next two afterwards.
mount.
Yeah,
You
that
have to
front
assume-
camera, we have to have a mount.
You have to assume that part, you know, it's like WF.
Why do you want
or
front
that
camera now?
for image
detection and.
You can do it with
Cross.
First get that thing flying, then we will worry
It
about.
all depends on the orientation.
Mhm.
Like if
We
you,
can do image detection
You
with
know
that.
if you're assuming that is more generic essentially. What, that's like a overall. That would be what you say.
I'm curious to learn more about so
So.
the accelerometer
The only-
sensor gives us the body frame body frame values. But for our calculation, not at the same controllers or anything, when we need the state values in the position, like the global frame. So we use those different equations with the help of rotation matters and everything, we convert the values. I mean, obviously after filtering, we convert them into global frame and then we.
So
How does sensor?
Basically, sensor fusion means you are getting two independent measurement of the same quantity.
Yeah, that is it.
And then what you do is you combine those together. That is the fusion.
Yeah, so I am aware of what it is, but let's say for a value of P, like we get two sources for value of P. And we have only one differential equation which uses P to convert a corresponding global value. So we just have a single equation, but how does two values of
You
P?
get solution of P from the accelerometer. Okay, you get solution of P from the GPS.
It's a total.
Yeah.
It's a total of that.
Option P which is used in that.
You can take a simple average.
Both the back.
Oh,
That
oh,
will
okay.
better accuracy than just.
Yeah, so
But many times
it's,
what
it's, I guess
Yeah, so.
my,
Yeah.
my simulation just doesn't update. So, twenty twenty-two feet.
Square.
Big, okay, so.
Go back.
I don't know if it was that.
it
Yeah, that's
pops up
I don't
with
know that
this.
it boils down to this.
I come in.
that solution at the end that boils down to this.
I drop down, you
Great,
get
thank you.
percent,
I guess.
happens if I pause, it updates. Now, I thought that maybe I was missing the draw now. I have the else draw body, right? So I recall that at every time step that isn't zero.
One question.
And then
Well, actually, two.
I have
First,
the, else draw
I
now,
might just redo.
where I
this.
set the handle every
I
time.
didn't use these variables here.
I don't
but
know if
might
I'm
just
doing
create
something
the
wrong.
ones
Same as that
just
code.
using just kind of-
Yeah,
Is that the same if else statement?
and then
that we use?
it is.
what I just said
So-
is one.
Yeah, that's fine.
That's fine.
I don't know if I'm doing
As
something
long
wrong.
as your aircraft is looking like an aircraft,
Okay.
I'm okay.
Okay,
So I
It
was
should
having
not
a
look like a
thing
spacecraft.
okay.
where,
And then,
so
second
I'm
one I
running
wanted
it
to ask was,
paste, because otherwise it just.
four is asking us to
Oh, that's
change.
correct.
It should just be running. continuously,
not
That's why
but
pacing is why it's stopping.
the steps on
It
which,
run. I wanna see what
parts are done,
happens.
so instead of going from. Rotation to
So
Right now, you're,
rotation to
oh, so I
transition,
just crashed right
translation,
there.
it wants us to
Yeah,
go
so it
to
stopped.
translation. then
Okay,
rotation.
I don't-
Something
know
in your
how you
runtime
begin
will
that
simulate.
process?
Oh, come on, yeah, figure it out, man. I gave almost
Right.
50% of the solution.
It
We'll
just
just,
finishes.
Change the order.
to just change the order. of
I don't get
It's
any.
not like,
I
because
don't
I
get any
thought
error.
that would change.
Am I simulating?
That would change the,
No, not at all.
the body frames from the.
Nothing else, just the order of the frame. I mean, order,
It's the map sim, right?
You'll figure it out.
Okay.
If you go line by line through the code.
I think it's
you
one of
see
your.
that first it does rotation, then
It's one of the settings.
the second part of code, it's actually asking you to do
think.
the translation first time.
Okay.
So just change the
Full
sequence.
fast restart.
It's
Let's
okay,
try
yeah,
it.
then it won't, okay, because I was thinking in my head that if it's not.
No,
set
don't
up,
overcomplicate. No, everything else remains the same.
Okay,
It's a
You're
very
missing
simple
quite a
change
few
in the code.
boxes.
Don't change the
So
coordinate.
I don't have the,
okay.
I don't have these
PNP.
pre-feeding. I don't know what those do. Can I see what the timer settings are?
Right,
Yeah, that's what I was gonna check next. Is this guy
these two,
clock?
and they're like
Yeah, it's the
exactly.
same.
Should be about that. It's
Okay,
default.
information tag, yeah.
The only change that I heard. is
Um,
that my list of-
You're giving the pi over 180.
Yep.
Those three.
Yeah, they function
Drop plane. You have to drop
accurately
plane.
when
Let me
I,
just try giving these
Yeah, drop
constant
plane
values
at
and the
the
PEPN, because those are what
those are the translations, yeah.
so the fact that you're not feeding them anything, might be why. Also, you have inputs to these, but there's no input where it should just be constant. So
I just did put the gain,
like see
What
here.
too many output
Mhm.
parameters.
whichever vector is 1D. Is that what you're doing? Go to the bottom.
This needs to
Sure,
have
that's fine.
one position role.
so the,
Your
I,
manual
they're,
input
I just did them as gain sliders.
You look
Should
at
they
it.
be constants?
Yes.
For
So that's why it's stopping.
13.
I mean, I think you could do
parameters.
gain sliders too, but I don't understand. I think
Such a
maybe just
six.
try it with
So
constants
you just
first.
have it for six.
Sure, okay.
Yeah.
Constant into a gain slider, because I think these are gain sliders.
Yeah,
Block parameters, okay.
Okay.
Yeah, so I
Or
think
seven,
the fact that you don't have, look at like all these empty inputs.
Right,
is
it's-
Why
it's
it's not
getting upset.
running.
Yeah, if you have 7 parameters.
So, yeah, the
So
first three add constants into those, and then
Because
change
some-
those three in the bottom for
Change
just
other
plain
parameters.
constant, that you set to 0 for now, we'll change this later.
I mean,
Okay.
I wrote this.
because
all
it does
myself,
run. So when I did the pacing,
I don't know.
it does, when I pause it, the time step does increase. Which is why every time I pause, it changes. It just doesn't do that continuous update.
Could just be Simulink in your computer, but let's try this first, just
So
because I
I-
think you might need those constant inputs.
Yeah, I ran it on this machine,
I
a virtual
really
machine, and
don't know
my home
Why?
machine. So it's something I'm
where the
doing.
error is.
I
If you have-
can't. I
If you want to
can't
see
blame
my
the
code.
Although, you know,
you're looking to see the code.
if I can put that on my assignment, I'll just do that.
Could it possibly
it's
be
not
with,
too-
so.
Is your
No,
spacecraft working?
Really, the submission's
Yeah, I
gonna
would
be like,
I would
if
make
your
sure that
space,
the
if you can
spacecraft
show
is
you can
working.
change the angle in your spacecraft, that's all you need for this assignment.
Cause I
Right.
divided each of
So, I
the
mean, you
points
have the
first in,
assignment
like, our
done,
own
is what I'm
vector, and
saying.
then I put the
Okay,
vectors and
it's
just
just like,
No
calculated,
constants there.
matrix like
Just
this.
delete
But-
all those and then put
I'll-
constants there instead is actually
So
what it
let me
is.
ask you this, did you download the code from GitHub and then
really wish
used
I
it,
wouldn't
or
do that.
how are you?
Yeah,
using
I'll put
it?
this there, same with the
I
bottom.
know you tried to write this all by yourself, but the spacecraft code, did you get it from GitHub?
I got the code and it still didn't work because of the
and then these three as
erase
well.
mode.
Yes,
I'm on the 2022 version, so for some reason it didn't accept the erase mode modifier on the patch.
What you do is copy the code, paste it.
Oh, 2022
Oh, you got-
says
you
the
got it
erase
working?
mode is
Huh? You
deprecated.
got it? working?
Yeah.
I got it.
Yeah,
working.
It's
Like, I
still
just
used,
copied
but
what is there in
it
the-
pops up a warning and says erase mode is going to be removed in a future.
After
version.
that, you told me it's already there.
seems
I was like
I didn't
full
even-
seeing through the
Oh,
entire
it
code. what
stopped
it is.
again.
Oh, yeah, it did.
Okay,
Yeah, I don't know what the issue is, but I'm sure Jacob and Tatvik should be able to figure it out because
Yeah, it-
I would start with the.
I don't know, that's the
GitHub,
end of the world. It's just odd.
Code.
the fact that it's not constantly simulating, yeah, I'm trying to think, it might just be some small setting in MATLAB.
Yeah, it has to be something I'm doing. That's just, I even tried increasing my stop time.
Yeah, because right now his is just running and dying.
So
And then you're dying.
And I remember you giving
So
us
I hit
this-
run and then it just, it compiles and then it ends.
What does the diagnostic say?
So if I change that and then hit run, it'll update. It's just the simulation's ending.
Weird. That'd be
So
like a small setting, right?
do you have hold on?
yeah, it gives me the erase mode property is no longer supported and will error in a future release, which, okay, you know,
So just go to simulation pacing and try to adjust the simulation pacing.
That's what it was working kind of.
so if I do simulation pacing and, you know, there,
Do you have the hold on?
yeah, Yeah,
Okay,
the
okay.
figure doesn't disappear. It just, so now,
Tatvi, can you help her with the code?
so now that I've done this, right, I can, okay, -32. And the simulation's still running. I've updated the parameter. And then if I pause, it inverts. But
You think
only during.
2022 might be an issue. Oh, that's what you're running on, isn't it?
No, I'm doing on 2021. But others got working on 2022.
Okay,
Yeah,
so
it-
it
and
might
I-
be a small setting issue then.
And the virtual version that you can run online is 2021, and I ran it in there too. With the way that I did this. So it has to be something I'm doing. I'm not sure what. I can send emails. I don't want to keep you here all night, but
Yeah, just look in the code too, 'cause it's probably just some small setting like